Returning to complex numbers then. There's this thing called Demoivre's theorem, which you already know, but you just don't know it's Demoivre's theorem. Because really it just says this. If you raise a complex number to the power of n, then the argument gets multiplied by n, which we already know. But it formalises it into a theorem. But note, Demoivre's theorem actually is for modulus equals 1. Mind you, it's very easy to extend that out because all we're really doing is multiplying by r, and we know r to the power of n is r to the power of n, so we can easily extend that to any complex number. So if I want to expand out 1 minus I to the power of 5, sure, I could use the binomial theorem. I could write out all 6 terms, collect like terms, and do that. That's definitely a way of doing it, but this now gives us another way of doing it. The modulus is the square root of 2. The argument for this one, minus pi on 4. So now we're saying, well, it's root 2 cis minus pi on 4 to the power of 5. And by Demoivre's theorem, well, root 2 to the power of 5, but then we multiply the argument by 5, so we get minus 5 pi on 4. Let's tidy that up. 4 root 2 cis 3 pi on 4. You'll notice I've converted the minus 5 pi on 4 into the principal argument. So if they want the answer in mod arg form, then I would always change this to the principal argument. If, however, we're just working out 1 minus I to the power of 5, I don't actually need 3 pi on 4, because minus 5 pi on 4, of course, will give us the same answer. So it comes down to what form they want the answer in. And we know that's going to be minus 1 on root 2 plus 1 on root 2i, and there's our answer, minus 4 plus 4i. Which way is quicker? Expanding out using the binomial or doing that? Well, maybe for something like power of 5, the binomial theorem would be quicker. But as those powers get bigger and bigger and bigger and bigger, obviously this technique becomes more efficient. But it now allows us to go back the other way, and that's finding roots. So yet another way of finding the square root of numbers. Because if we know z to the power of n is x plus iy, we can change that to mod arg form, becomes r cis theta. So even though Demoivre's theorem was where n is an integer, it still works when it's not an integer. So I could say z then will be the nth root of r, but then I would divide the argument by n. This is like saying to the power of 1 on n. Notice though, I've also added in 2 pi k on the top, because when we're talking about roots of a number, we have more than one. Square roots will have 2, cube roots will have 3, and so on. So the 2 pi k in there just takes into account for the fact that, hey, I can go around the circle 2 pi radians and I'm back at the same spot. So I just add multiples of 2 pi and then 0, 1, so on, up to however many we need to get the right number of roots. Now a little trick here is if your solutions will end up in conjugate pairs. So if you're finding the root of a real number, then instead of going 0, 1, 2, 3 and so on, go 0 plus or minus 1, plus or minus 2, because the plus or minus will get you the conjugates straight away. Right, z squared equals 4i then. I want to find the square root of 4i. Oh, well, I can now say that that's 4 cis pi on 2. So my square roots will be 2, because 2 being the square root of 4, cis 2 pi k plus pi on 2, all over 2. I only need 2 solutions because of square roots. So I'll sub in 0 and I'll sub in 1. And that should get me the 2 solutions. So I end up with 2 cis pi on 4 and 2 cis 5 pi on 4. I know what they are because they're nice exact values, 45 degrees. So 2 times 1 on root 2 plus 1 on root 2i, and 2 times minus 1 on root 2 minus 1 root 2i. Tidying that up, there's our 2 answers. So root 2 plus root 2i minus root 2 minus root 2i. Now, this idea works really well when we end up with exact values, of course. If those arguments end up being, I don't know, pi on 7 or something like that, it makes it a little bit difficult now because, what's the exact value for cos of pi on 7? You can work it out, but obviously there's a lot more working out to find out what those exact values are. Another way of thinking about it, though, is visually. All you really need to do is find the first solution. So there's my first solution, 2 cis pi on 4. But remember, we're adding on multiples of 2 pi k divided by whatever it is. So they should end up being evenly spaced around the diagram. So with the square roots, they're always going to be 180 degrees apart. So there'll be reflections of each other through the origin. Therefore, the other one is down there. It's got to be 2 cis minus 3 pi on 4. And then obviously you can work out what those are. But that's another way you could think about finding them. But we're not restricted to square roots now. I could find effectively we're finding the 4 roots of 16. Now, before complex numbers, we would have said, oh, well, there's only 2 answers to that, of course. Find the 4th root of 16, you'll get, is it 2? 2 to the power of 4. Yeah, that's 16, isn't it? Okay. You get 2 and you get minus 2 as well. But there are actually another 2 solutions. So let's have a look at it. The x to the power of 4 is 16. Well, 16 is the same as 16 cis 0. So this will be 2 cis, well, it'll just be 2 pi k on top, because 2 pi k plus 0. I'm dealing with a real number, so you know I've gone the plus or minus technique on this one. So I'll have 0, plus or minus 1, and also 2 as well. I'll end up with 2 cis 0, 2 cis pi on 2, 2 cis minus pi on 2, and 2 cis pi. All of those I can work out. I've got 2i, minus 2i, and minus 2. What would that look like on our diagram? Well, the first solution is over there at 2, but we know they will now be every 90 degrees apart, because 4 solutions in the circle. The next one would be there, 2 cis pi on 2. Next one would be, oh, I've done the conjugate, haven't I? So the next one's the conjugate, and then there's the other one. So all 4 evenly spaced around a circle. Find the 4 fourth roots of 1 plus root 3i. Well, let's work out mod arg. It's 2 cis pi on 3. So I'm going to be going the 4th root of 2. I don't know what that is, so we'll leave it as 4th root of 2. Pi on 3 plus 2 pi k. In this one, I'm going 0, 1, 2, 3 because, well, there's no point doing conjugates. They're not going to appear in conjugate pairs. You could still do the plus or minus if you wanted to, because essentially you're just substituting in 4 consecutive numbers. You could pick any 4 numbers you like. You know, it doesn't have to be 0, 1, 2, 3. If for some insane reason I wanted to, I could sub in negative 20, negative 19, negative 18, and negative 17. It will come up with 4 solutions. There are my answers. The advantage, of course, of using 0 and 1 and numbers like that is it'll get it into principal argument very quickly. Bigger numbers you're subbing in, they're not going to go into principal argument. And that's what I was saying before. If you are going to leave your answer in mod arg form, which I am in this case, then you go back to the principal argument. So the first one's okay, the second one's okay. 13 pi on 12 becomes minus 11 pi on 12. 19 pi on 12 becomes minus 5 pi on 12. So how would that one look? Well, there's my first solution, every 90 degrees. So there's the next one, there's the next one, and there are the 4 solutions, and we can quite easily see, yeah, we don't have conjugates in this, but they do all lie on that circle. The 3a.